All right, so friction, as we saw in the last brief lecture, is basically a nuisance to us in our attempt to understand how objects move and what physical laws govern that motion, essentially how inertia works. And so we want to kind of think about scenarios where we can mostly neglect friction, where friction is small enough that we don't have to worry about its effects as much, and our intuition of a situation kind of accurately reflects a low friction environment, and that will help us see the actual workings of inertia. Right? And so one way to do that would be to conduct thought experiments of us floating in outer space, but maybe a more prosaic terrestrial example would be for us to strap on a pair of ice skates. I am from the northeastern US, after all. So ice skates, or rollerblades, or skateboards, if you like, they don't completely eliminate friction. They just make it much smaller than the effects of friction when we're wearing shoes or when we're barefoot or something. And by reducing friction to a point where we can, for the most part, neglect it at some level, they really help us with our intuition, right? So if you're wearing a pair of skates, for instance, then if you just push off once, you'll send yourself gliding a good distance. Eventually, of course, friction takes over and grinds you to a halt, but in the first little bit, you kind of coast freely and life feels good. Right? So in this section, we're going to go even farther and imagine somehow a completely perfect pair of ice skates, a set of ice skates that somehow take the amount of friction they experience all the way to zero. In the same manner, we're also going to ignore things like air resistance, right? So now, if you take a single push in these perfect ice skates, instead of just coasting for a good ways, you will actually coast indefinitely in the same direction until either you bump into another object or you exert more forces on your environment. With this kind of scenario in mind, we can actually restate the property of inertia in terms of the way an object's velocity, or our velocity in these pair of skates, actually behaves. Okay, so this is Newton's first law of motion. Newton's first law. Right, and Newton's first law says that an object's velocity will remain constant unless that object is acted upon by a force. Unless acted upon by a force. So this is often said, an object will continue to move at a constant velocity until acted on by a force. And, we can contrast that with our statement of inertia. An object in motion tends to remain in motion, an object at rest tends to remain at rest. Here you can see that tendency. Unless there's a force, an object's velocity, both its magnitude and its direction, will remain constant. And that at rest part of the clause is actually just a special case where, from before, at rest is just velocity equal to zero. And I didn't emphasize this at the time, but throughout the rest of this course, when we're trying to make sure when we're trying to give a notation that indicates we're talking about a vectorial quantity rather than a scalar quantity, I'm going to write it as the letter, for instance, the velocity, with this little arrow on top, right? So the arrow reminds us that this quantity has both a magnitude and a direction, but zero is a kind of very special case where, since the magnitude is zero, you don't need to specify the direction. Zero velocity in any direction is completely equivalent. Right? Okay, very good. So this is Newton's first law. An object will continue to move at a constant velocity unless it's acted on by a force. And to kind of summarize what we've talked about so far between inertia, friction, and the first law, our intuition for all kinds of everyday occurrences, like pushing a book across a table, for instance, says that we need to continually push an object in order to keep it moving. We need to continually apply a force just to maintain a particular velocity. The laws of nature, on the other hand, tell us that an object will move at a constant velocity when no force whatsoever acts upon it. And this apparent conflict is resolved by acknowledging that there are other forces acting on the object. In this case, friction or air resistance have a tendency to slow an object down and oppose its motion. But in the absence of all of those other forces, for instance, us wearing our perfect ice skates, an object that experiences no other forces acting on it will continue to move at a constant velocity. Okay, so that's Newton's first law. Let's ask ourselves then, what is the relationship between if objects have velocities that stay constant when no forces act on them, what is the relationship between changing velocities and forces acting on an object? So this is section actually 2.2.1 of the lecture notes, accelerations and forces. Accelerations and forces. Okay, so if Newton's first law tells us that velocity is constant when there's no forces acting on things, what happens to our hypothetical ice skater when forces do act? Well, we all kind of know, at least at some level, the intuitive answer to this. If something pushes on us, our velocity changes, right? And we've seen before in the first chapter that we call the rate at which an object's velocity changes over time, that object's acceleration. Right? And so again, acceleration is a vector quantity, just like velocities and positions are. And I want to pause here to kind of make this point that in the English language, we have kind of specialized words that refer to accelerating in the same direction that our velocity is moving. We call that actually just acceleration. And acceleration in the opposite direction. We call that deceleration, right? If we're moving in a direction but we're slowing down as we move in that direction, we say that we're decelerating, right? In physics, there's no need typically for this kind of multiplication of terminologies. And so we say that any change in velocity corresponds to an acceleration. So first, let me make the point that any change in velocity is an acceleration. And remember that velocities, sorry, there's a little bit more lag today than usual. Velocities are both a magnitude and a direction, because they're vector quantities, right? Magnitude and direction. So for instance, if I have an object and it's moving at some velocity in this direction, so I might say the velocity, let's say this is like 1 unit to the right and 0 units to the left. So if I accelerate in the same direction of velocity, then sometime later this object will be moving faster. So if this is our initial velocity, maybe our velocity in this blue arrow is some greater quantity to the right. So we've accelerated in the same direction we were moving, we got faster. But in the same way, suppose in English we might say we decelerated a little bit. That's an acceleration too. Here, acceleration is in the opposite direction. Right? So we've accelerated against our velocity, so our velocity has changed in the direction of the acceleration, which was the opposite direction we were moving originally. So in this situation, maybe v is a little bit smaller, and we've decelerated. Maybe this is a half. Okay. But you could also say, what if at some point in time you're moving, 1 meter per second to the right, and then you turn, but you stay moving 1 meter per second, maybe now in this direction. Still, you've undergone an acceleration because your velocity, which is both the magnitude and the direction, has changed. So an acceleration in a direction which is neither along your velocity or against it corresponds to a change in the direction your velocity is moving. It corresponds to a change in angle, if you like. Great. So all sorts of changes in velocity correspond to accelerations, and these are the kinds of accelerations that we experience when forces act upon us. Okay. So anytime, let's say we want to know more details. How much do velocities change when lots of different forces act on us? An important property of objects is that at any moment in time, they only have one acceleration. So if I'm experiencing multiple forces, I don't have to consider adding up multiple tiny accelerations. What I can do instead is add up the total forces acting on me, both their magnitudes and their directions, and then compute a total acceleration that I experience as a result of all of the forces, right? So it doesn't matter if I'm experiencing, one big force to the right or 3 smaller forces to the right. If the total amount of force is the same, which you can evaluate by adding up all of the vector forces, then my total response to all of those forces will be the same. Okay. So let's draw, I guess, a few pictures. better yet, let's make use of the fact that I've already drawn a few pictures. Here's a few extremely amateurish cartoon illustrations of, say, people trying to push around a block on a smooth surface, right? So if we focus on this first example, for instance, here's a side view of all these situations. Here's a top view. You can see that I have one person pushing this block to the right with some force. And so this force is the only kind of interesting force acting on the block. So this force is the net force, which I'll write as like F net. Okay. Now, in this situation B, now we have two people that are pushing in two different directions. So I have person one, over here, pushing, this much in the direction to the right. I have person B over here pushing this much in the direction which is up on this top view. And the net force you can get by adding these two vectors together. And so the net force here is just the sum of these two forces. And remember, you could also kind of compute that net force vectorially by, taking the two vectors and translating them head to tail, so that you take the vector for F1, force 1, and add the vector for force 2, and then you get this kind of final net force, which I've drawn in red here a little bit more clearly. Okay, so if you have one force acting in a direction, things are very simple. If you have multiple forces acting in multiple directions, you just add the arrows corresponding to all the forces together. This third case here corresponds to, well, what if I have two people pushing in opposite directions? If person 1 pushes to the right with force 1, and person 2 pushes with force 2 to the left, and if those two forces are exactly equal to each other, they're pushing exactly as hard, then in fact the net force on this object is 0. Net force, If one person was pushing a little bit less hard than the other, then you would do the same trick we talked about up here. Suppose F2 was a little bit shorter, so I would take F1, and then I would take the start of F2 and add it here, and I would discover that my net force is just this small leftover piece here, if the forces were unbalanced. Okay, and so this is a very general strategy that you can use when an object is experiencing multiple forces at the same time. You kind of think about all of the forces that are acting on an object, you add them all up separately, and then you compute, by adding them all up, the total or net force acting on that object. Okay, and why do we want to go through the trouble of computing these net forces? It's because the acceleration of an object, so if I write that as this acceleration vector, both the magnitude and the direction of an object, has the following relation. It takes whatever the value of the net force acting on that object and divided by the mass of the object. So the acceleration of an object is equal to the net force, which is also a vector, divided by that object's mass. Okay, and this is Newton's second law of motion. So Newton's second law, okay, which says that the vector sum of forces F vector, and maybe I'll write a little net subscript down here just so that we remember it's the total sum of all the forces acting on an object. F net is equal to the mass of the object, the mass m, multiplied by the acceleration. Which we write as this a with a little vector hat sitting on top of it, by the acceleration of that object. This law, Newton's second law, is often summarized as, force equals mass times acceleration. Okay. Now you can see that this expression of Newton's law is completely equivalent to what I wrote up here. It's just, you move the m from one side to the other. I actually like to think about Newton's second law conceptually in this way, though, because it kind of keeps the cause and the effect kind of nicely organized in your mind. The cause of an object's motion is a set of forces acting on it, and the effect is as a result of those forces, you experience an acceleration. So the acceleration of an object is caused by forces, and the amount that you accelerate is set by the force divided by the mass, right? This framing of Newton's second law, which is kind of historically how we always talk about it now, is equivalent. It's just a rearranging of an algebraic equation, but sometimes it confuses people because it kind of seemingly flips the role of what is the cause and what is the effect. So this law, which is a statement, again, about how the world works, how do objects move in response to forces, tells us that the more massive an object is, for instance, the more force you need to apply if you want to accelerate it by the same amount, right? And this, I think, feels pretty intuitive. If you can, throw a baseball a certain distance, your arm can exert up to a certain force on a baseball to launch it on some trajectory, and you try to repeat that experiment not with a baseball but a bowling ball, you'll find that the baseball you can accelerate much faster than you can accelerate the bowling ball, right? Similarly, if you strap like a rocket engine to a sled, you can accelerate a sled much faster than strapping that same rocket engine to, say, an actual rocket. Okay. So I guess there's one other thing that I want to talk about in this section on Newton's first and second laws, and that's frames of reference. So this is section actually 2.2.2 in the lecture notes. Frames of reference. And what do I mean by this? So imagine you're skating on a frozen river, right? And as you skate, from your perspective, you could imagine that you are still and the world around you is moving past you. The scenery on the riverbank is moving past you, so on and so forth. On the other hand, someone who's standing on the riverbank, not moving, sees the world very differently. They see themselves as motionless, they see the scenery as motionless, and they see you kind of gliding past them at some velocity. Who's right? Fortunately, everyone's right. In physics, we would say that both people in that situation, you coasting at a constant speed or someone staying still on the riverbank, are viewing the world from different inertial frames of reference. Inertial frames of reference. Which is a way of saying inertial frame of reference is basically a point of view of an object that is not accelerating and thus is moving according to its own inertia. It's moving at a constant velocity. So from the point of view of an object moving at constant velocity. No accelerations, right? And it's a remarkable fact that the laws of physics work perfectly well in any inertial frame of reference, okay? So if you watch some event happen from your inertial frame of reference, you'll see all kinds of stuff. Objects moving around, you see forces being exerted, you see other objects accelerating, all according to the laws of motion. For instance, the first and second laws of motion that we've just seen. Somebody else, watching from their inertial frame of reference, will also see objects moving, forces being exerted, things accelerating in perfect accordance with the same laws of physics, okay? Now, the details of the values you assign to different quantities might be a little bit different, but you can each completely explain what's happening with the same fundamental set of laws, So for instance, let's pull up, I guess, another picture. That appears in the lecture notes. Suppose you're standing on the side of the road and you watch your friend drive by in a very cool blue top hat, moving at some velocity in some direction, So let's say the car is moving at a constant velocity, so both you and your friend have separate inertial frames of reference. Each of you is moving at a constant velocity. You're moving at zero velocity, maybe your friend is moving at, v is equal to 48 miles per hour to the right. And let me give you an example of the kinds of things that I mean when I say you might disagree on the precise quantities, the physical quantities you might measure in your separate inertial frames of reference, right? So for instance, in this scenario, you see you see your friend's hat moving at a velocity of 48 miles per hour to the right, just like everything else in the car. But you see that it's not accelerating because you don't observe any forces acting on it, right? So to you, this car and everything in the car is moving at 48 miles per hour to the right. On the other hand, from your friend's perspective, things are very different. It's still true that, for instance, there's no forces acting on her hat, and so she doesn't see it accelerating. She sees its acceleration as 0. But she also sees its velocity as 0. It's sitting motionless on top of her head. In contrast, you don't look like you're standing still. You look like you're moving at some 48 miles per hour in the direction opposite to the direction she's moving. Okay. So the fact that physics has this amazing property, that as long as you pick an inertial frame of reference, the same sets of physical laws suffice to explain everything that's going on, that gives us freedom to pick the easiest frame of reference to work in. And usually we will do this in this class without really even thinking too hard. It will be very natural for us to pick a frame of reference that makes the problem at hand as simple as possible. Right? Every once in a while, though, as we'll see throughout the rest of this course, we'll run into some extra difficulties, and we'll have to think harder about what that best choice of frame of reference really is. So we'll see a few examples of that in the rest of this course, so I wanted to just make sure I brought it up now. But what we have to remember for the time being is the following. We kind of saw that, especially when you neglect friction, it's easy to understand inertia, and you can restate the effects of inertia as Newton's first law. Objects have constant velocity unless they're acted on by a force, and the precise way that that statement is changed by forces is encoded in Newton's second law, which says that the acceleration an object experiences is equal to the force, the net force that object experiences divided by its own mass, or equivalently, force equals mass times acceleration. And we can choose any constant velocity frame of reference that we like to analyze different physical scenarios. So we'll make use of that throughout this course to make the math as simple as possible.